You can see it a little bit better. So we're starting with this mathematized question to warm you up. This is a sequence of step functions. And we talked about sequences of step functions before, and we had all sorts of nice things. But this one has something weird going on, something not nice. And so that's what we're trying to figure out. And we want to recall, so we had this idea of pointwise convergence, of going to 0 for every single x value. And then the thing we're actually interested in is integrals of these things. Now this one's a step function, so the integral is just given by base times height is nice. But we want to put this thing in the context of theorem 2.2.6. That was the last big theorem we proved about sequences of step functions. And theorem 2.2.6 was going to let us define the Lebesgue integral using the definition we've been talking about. So what does theorem 2.2.6 says? It says if you have a sequence, a certain sequence of certain step functions, and certain things happen with the limit, then certain things will happen with the integral. And what I want you to do is think about what's going on for this sequence and put it in the context of theorem 2.2.6. And this is a word box where you can give me any kind of thing. You can say, I have no idea. That would be something you could say. You could say, yes, it applies. You could say, no, it doesn't apply because blah, or just no blah, and then the reason why. So you can write anything you want over here. But I just want you to think about this sequence of functions. Drawing it on a piece of paper will help you out. This is the kind of stuff we're going to be looking at. Any questions or comments about the problem before I set you loose on the problem? Yeah, and once again, the code to join is here. Today, the code is YO. 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 Okay. Questions, comments? All right, let me give you like 2 minutes to think about this, draw your little cartoon, and to start with, before I reveal, here is my sketch of these things, which I drew in my favorite graphing calculator program, Desmos. So this is supposed to be a representation of the functions fn. Let's put it into nice contrast. So in green is the function fn. This function here is f1. The function f1 when n equals 1, it's 1. Of course, it has the filled in dot over here and the open dot over here. It's the so-called CAD-lag function that we talked about. And as you increase, two things will happen. So when n equals 1, okay, let me, let's make these little step by 1 so that the n is always an integer. And then okay, there's n equals 2. N equals 2, then it's, the value of the height is 2, and now we're going from a half to 1. And then when n equals 3, I don't know, it took away my slider. I'm so sad. Why did it take away my slider? Give me my slider back, okay? All right, here we go. Okay, I guess I'm going to start at 1. And go to 10. Okay, what? There's 2. There's 3, right? So it's a width of a third, but height 3. And then a width of a quarter, and height 4, 5, 6, and so on. And now we can really play the fun animation. Let's go up to 100 and hit play. And it will animate for us. What's going on is this thing gets taller and taller and taller, but narrower and narrower and narrower. And that's the kind of tricky function we're looking at today. This is kind of a pattern we've seen a few times before and is a common theme in this kind of tricky function, things that can go wrong. Okay. How many people had something like that for their sketch when I said draw a cartoon? Okay, great, fantastic. Let's now go and see what the answers were or what people said. And let's start with this one. True or false? Is it going to 0? 10 people said true, 8 people said false. So pretty split on this thing. So for every fixed x, we're doing the limit. So this is a kind of you have to put yourself in the right mental space for what's going on here. Because when you see this kind of thing and you have your little cartoon, you're kind of looking at the entire function all at once. But for the question I just asked, the true-false question, we're talking about for a fixed x value. So let's put a fixed x value on the screen. Let's do the x value 0.7 comma 0. Or here, actually, let's make it a nice line. X equals 0.7. Okay, so there's a nice little line. And let's make it a nice dotted line so we don't think it's a thing. So we're at some particular x value, x equals 0.7. And we're looking at the values fn of x. Fn of x is now just a sequence of numbers. So you forget about functions, which are in green, and just looking at the height at this particular x value will give you a sequence of numbers. And now you're back into first year calculus, right? Thinking of sequence of numbers. Is that second year calculus? Whatever. You're into toddler stuff. Okay. So what sequence is it? So when n equals 2, we did this one. Actually, we can go all the way down to n equals 1. This is just like we did before, except instead of looking at the whole function, I just care about the height right here. So first it's 1. So 1, first thing on my sequence, let's write this down. 1. What's the next thing? The next thing is 2. Give me my slider back, you beastie. Okay, 2. 2. So now it's half the width, but we only care about the height here. That's 2. 2. Then what? 3. Okay, 3, height 3, right? Dotted line, height 3. 4, here comes 4. I think I see the pattern. 1, 2, 3. Can you guess what's going to be next? 0. Okay, 0. See, because the box missed the line, okay? So this is a pattern we've talked about before. That's very common, is, right, something can be happening sort of on the x values and the y values. And then what will happen at a particular point depends on both, right? Depends on both the height of the boxes and where the boxes are. Very important. So people were pretty split. I have not yet revealed the answer to this one. So about half the people said true, about half the people said false. Let's do a revote. I think this is an important one. So I'm going to revote this, and then we'll see what happens. I have to click here, and then I click this. Repeat exercise. Let's take a look. This time, after revoting, we have 13 people in true, and true is the correct answer. So very, very good. I think people see this thing. This is a really important idea to keep in mind, is that when you look at a fixed x value, right, if the boxes miss you, or if the action in the function kind of goes by you eventually, then you'll see whatever you see in the fixed thing. And so even though this function is kind of like, in some sense, blowing up, from the point of view of any individual point, it is eventually, not only is it going to 0, it's eventually 0. So the sequences always start with 1, 2, 3, but then at some point they switch to all zeros, and then they are zeros forevermore. The limit is 0. Okay. This is a really important example to make sure you 100% understand. Are there any questions or comments? Maybe somebody who, especially if you voted false the first time, what was the thing you were missing? Is there anything I can clear up? Okay, people seem okay with it. Very good. So the next interesting thing is, what is the deal with the limit of the integrals? All right. Wow. The limit of the integrals equals 0. 67% of people said true, and the answer is false. Let's do the limit of the integrals. For this one, you have to be able to do the integral of this little rectangular function. Okay, this little rectangular function. And the integral is just base times height, because these are step functions. For step functions, the integral that we use is base times height, and you just got to add up over all the boxes. Mercifully, this function only has one box, so you just got to add it up. What is the area of this thing? Let's put it on, get some chalk out. Okay, this is what we're going to be saying, but let's do a little scrap work over here. What is the integral of fn? The integral of fn equals base times height. What is the base and what is the height? So this is for the function fn, which is n times the indicator from 1 minus 1 over n. Oh no. 1 minus 1 over n to 1. So what is the base and what is the height? Anyone do it this way? Yeah. The base is 1 over n. Yeah, and what did you say the height was? N. Base times height. So the base was 1 over n, right? It's shrinking down to 0. That was the box is shrinking. But the height was n. 1 over n times n. Very nice calculation. You should get 1. So the integral of fn, no matter what n is, the base and the height are different for different n's. But the integral, which is the base times the height, that was cooked up in this problem to always be 1. Okay, so what is the question in the mathematize asking you for? It's asking you for the limit as n goes to infinity of the integral of fn. Fn is a function. The integral of fn is a number. This is an ordinary limit of numbers. And in this case, it's the limit of n goes to infinity of the sequence 1, 1, 1, 1, 1, 1's forever, right? It's always 1. It's the limit of the sequence of all 1's. What is that limit? It is 1. So the limit is 1. The limit is not 0, which a lot of people said. Okay, let's see Did people say, I wonder if people said 0 the first time. I guess probably. Can I see what they said the first time? Okay, yeah, most people said true for the limit being 0, but the limit is not 0. The limit is 1. Okay, the limit is 1. Okay, since many people did not realize that the limit is 1, and they think the limit is 0. If you thought the limit is 0, then you're probably like, oh yeah, theorem 2.2.6 is great. The pointwise limit is 0. The limit of the integrals is 0. Everybody's happy. But the limit was not 0. The limit is 1. So in some way, theorem 2.2.6, there's something funny. Something is not working. That's the discussion that I want you to have for this little text box. So now that we know that, this one was 0 and that one was 1, in fact, yeah, I guess I can reveal it. So true and false, and that means something weird is happening with theorem 2.2.6. And that's what I want you to identify over here. So the answer is theorem 2.6 is not working here. Why is it not working here? What is the thing that is missing? If you also have notes, maybe you remember sort of the idea of the proof. This is what I'm trying to jog in your memory, is what did we use in this theorem and why is it important? Okay, I'm going to open it up one more time. This time talk to your neighbors, have a discussion about what kind of text could go in this box. There should be a nice one or two word phrase that will lock it down and explain what is going on. Okay, let's do it one more time. Reveal counts. Okay, hopefully everyone was awake. Yeah, look at that. True. Oh, one person was asleep. Okay, true, false. Very good. Why or why not? Okay, so theorem 2.2.6 does not apply because theorem 2.2.6 says if we have a certain thing, then the limit of the integrals would be 0. And the limit of the integrals is not 0, so the theorem is either wrong or it doesn't apply. And the theorem is actually correct. We proved it. So why does it not apply? All right, told me in a dream. This is the kind of thing that you need, yeah. Okay, so some people wrote they're increasing, very good, increasing, and they're not less than 3. Not increasing, very good. If you wrote weakly decreasing, that's very good because that is the way we did it in class. So the condition that is crucial here that people have figured out, it's not increasing or weakly decreasing. This is how we wrote it last class. So this is a screenshot from what we wrote last time. Or maybe this is my notes. Well, I think I talked about this last class, that non-increasing really means decreasing, but you're allowed ties, right? So it could kind of be flat for a while, but the functions need to be going down to 0. And this was absolutely crucial in our proof, because if you remember the way we did this proof, actually, why don't we, because we have technology, we can just go to our actual proof. Okay, so if you remember, our actual proof involved this kind of picture where we were trapping the functions, right? The functions were slowly coming down to 0, and we were trapping them in two zones. There's the zone where they're kind of near the x-axis, where the value of the functions is low, and then there's this like bad zone where the functions are potentially tall, but that was very narrow, right? And we knew, because the functions are going down to 0, that they're not sort of getting worse and worse and worse in the tall zone. They're sort of as bad as they were at the beginning. F1 maybe was a horrible function that was height 1,000, but they're not getting worse and worse and worse, right? So the weakly decreasing is exactly this kind of thing that our thing is not doing. This example of functions is not doing the weakly decreasing because it is going to 0 everywhere, but near 1 it's getting worse and worse and worse, right? So there's sort of two things that are happening. It's getting better, it's getting closer to 0 most places, right? For every fixed x value, it's getting close to 0. But really close to 1, the issue is getting worse and worse and worse, and it's getting bigger and bigger. And the weakly decreasing sort of says, look, it can't get worse everywhere, right? It's at least the same, right? It's the same or better, it's not getting worse. So this is an example of what is called a monotone convergence theorem. Let's go back to today's note. Some people call this type of theorem, they call this is a type of monotone convergence theorem. And there are many different theorems that are called the monotone convergence theorem. One by, I think, some guy named Beppo, which is fun, we'll do later. But basically the idea in a monotone convergence theorem is like things everywhere are not getting worse, and eventually the limit is 0. And so if things everywhere are not getting worse and worse, then we can hope that the limit is 0. So this is absolutely crucial that the weakly decreasing is super important, needed. And you saw in the proof, the way it worked is we basically we're bounding, we're like, okay, something bad could happen on a small set, but the thing that happened on the small bad set can't be too bad because it's as bad as it was for the function f1, and so there's some m that bounds everything. So we're going to see versions of this. Okay, this is the thing I wanted to emphasize at the beginning and to sort of like warm us up with a tricky example. I think lots of people got it, and we have these convergences, weak convergence to 0, or pointwise convergence to 0, versus the convergence of the integrals. That's the kind of issue we're talking about. Any questions or comments about the theorem or the proof or the idea? Okay. Last class, we also did this upgraded version of theorem 2.2.6, which is corollary 2.2.7, which says, again, the fn's, if they are weakly monotone, this time they're the reverse. So in this one, in theorem 2.2.6, they went down, the functions were going down to 0. In this corollary, the functions are going up. So I don't know, the functions are going up, and they're going up to something greater than 0. They're going up to something greater than 0. The limit is greater than 0. The nice thing is, we don't need to know what the limit is. We just, as long as the limit is something, and that something is greater than 0, then the limit of the integrals is also greater than 0. You can make a reversey version of this, where you have a bunch of things going down to something negative, and then the integral will be negative. That will be useful. So this greater than is handy for our proofs. In fact, the next proof we're going to do, this is the main event today, is lemma 2.3.2, which says exactly this kind of thing, but we are getting rid of the weak thing, right? So notice in the statement here, no weakness, no weakly increasing. There's no monotone here. So we are getting rid of the condition that I just told you was so important. I said we're getting rid of it, and we're doing something exactly like that. So if f is tilde equals to a sequence of step functions, remember tilde equals. This was our definition of the Lebesgue integral. Here is a reminder of the definition of tilde equals. Right? We had this sequence of fn's that are step functions, and they have to converge pointwise to the original function f, except for this nasty set, and the integrals have to be absolutely summable. That's what we're doing. So we're upgrading corollary 2.2.7 to lemma 2.3.2, and the hard part is getting rid of this weakly increasing decreasing thing. Okay, but it says the same thing, right? So if f is kind of an infinite limit of the fn's, then the integral of the fn's has to be greater than 0. So if f is greater than 0, then the integral of the fn's sum up to something greater than 0. That's the idea. That's the big picture stuff. Questions or comments about the goal for today? That's what we're trying to do. And that's why I wanted to make a big deal about the weakly increasing decreasing. You see, like, this is really fundamentally what we're doing. Okay. Here is maybe thinking in terms of strategy. If we don't have weakly increasing decreasing, we just saw an example where weakly increasing decreasing was important, right? You need it. You can't just get rid of it for nothing. What are we going to replace it with? We're going to have a different sort of condition that's going to sort of replace weakly increasing decreasing. So no weakly increasing decreasing. We're going to replace with something else is going to sort of act in the place of the weakly increasing decreasing. That's going to, again, same kind of thing, like the weakly increasing decreasing, make sure things can't go too wrong. Things can't go too wrong. What could we replace it with? And again, it's something part of this definition we've seen a few times now. This tilde equals has a bunch of stuff baked into it. Which condition do you think is going to be the helper that makes sure things can't go too wrong? What do we have? Any ideas? I guess, okay, there's A and B. What else is there? I guess it's got to either be A or B. Yeah, I mean, okay, it's got to be A or B. Yeah.
It's going to be A.
It's going to be A. So this condition, again, you can read it as saying, listen, things could go bad, but they can't go too bad because this sum adds up to something less than infinity. In the example we just did, the sum of all the things is like the final function is n, right? And that's going to infinity. So this example is things are going bad, things are blowing up, the integrals are going to infinity, and in the condition that we're going to use today, we know things can't go too wrong because the sum of the integrals is less than infinity. So this is going to be our replacement, replaced with condition A. All right, condition A, and which is this guy. And this thing controls how bad stuff could happen. Controls how bad the effects can be. So the weakly increasing, decreasing was one type of control. This is another type of control. And you're going to see that actually the way we use this is we directly convert from the fn's into some kind of weakly increasing, decreasing sequence using the absolute values. Okay, that's the plan. Next up, we're gonna jump in and just prove the proof. Now you've seen the setup, you're mentally prepared, and you see the big picture of what we're doing. Questions or comments before we start? Okay, let us embark into this thing. Let me open my notes here before I say something stupid. Okay, so we're doing the lemma, the proof of the lemma. So lemma 2.3.2. So if f is tilde equal f1 plus f2 plus dot dot dot, and this tilde equal in it bakes in both condition A and B, i.e. A holds, the sum of the integral of the absolute value of the fn's is finite, n equals 1 to infinity, and B holds, which says some kind of limit as n goes to infinity of fn of x equals f of x, let's say for nice x, where nice means the thing that it means in the definition, but that's the general idea. Then if f is positive, the integral of the fn's will also be positive. Okay, and then once we have this greater than 0, we're going to upgrade it into kind of an equals in a moment. Okay, here's the proof. And the proof, here's the idea of the proof, is that, look, the fn's are not monotone increasing, right? That's what we have. We have a nice tool that works if the sequence is monotone increasing. The fn's are not monotone increasing. They go up, down, up, down, up, down. That would be bad. But you know it is monotone increasing. Okay, the idea is to use, let's write idea. Use the sequence of the absolute values. So we're going to look at the absolute value of f1 plus the absolute value of f2 plus the absolute value of f3 plus dot 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 dot. And this sequence is a sequence of step functions that is increasing because we made the f's positive. Okay? So the f's on their own are maybe positive or negative, and they're going all up and down, and that's bad. We can't control that. But the absolute values of the f's, those are strictly going up, and those are increasing, and they're not going to be too bad because of condition A. This is not too bad by condition A. Not too bad by condition A. Okay. Now, if you are worried, you might say, okay, but f has nothing to do with the absolute value of the f's, right? The original f, what we know about the original f is this condition. Okay, and crucially, I left out the sum. So it should be the sum from k equals 1 to n, because we're summing them up, not just looking at them, right? The f's are the things that add up to the absolute, the f's add up to f, right? f1 plus f2 plus f3, that in the limit is equal to the original function f. This silly sequence that you have made up with the absolute values, maybe you can control it, but it's got nothing to do with f, right? You took the positive and the negatives, instead of subtracting and adding, you made them all positive. So is this going to be even close to f? No, it's not. This is not close to what we need. But we can combine the two ideas where f is not close to this, so f is not close to that. But what if I do this? I'll do ordinary things with no absolute value for a while. Okay, and it will only let me erase one thing at a time here. Okay, so I'll do ordinary f's for a while for the first n naught. Okay, and now f is close to these things. And then afterwards, once I've done the first n naught, okay, that's finitely many pieces. Afterwards, then we do the absolute values. Okay? Plus 2, plus dot, dot, dot. So in other words, and this will really be approximately, this will be up to an epsilon. And this is the idea of the proof. So the idea of the proof is, if you add absolute values, then you convert it to monotone increasing, then we can use our theorem. And you can approximate f so that these things are very, very close to their things without the absolute value, and then f will be very, very close to this sequence. That's the idea. Okay, now we're ready for the actual proof. So that proof, as all good proofs do, starts with let epsilon greater than 0 be given. And what we are going to do is we're going to start by choosing an n naught so that this approximation is quite good. So in our approximation, we want all the stuff that we add at the end, we want it to be pretty, pretty small so that it doesn't really affect this thing. F is equal to the sum of the f's, and if we replace f's with absolute values, it won't matter much if those things are very small. So, so epsilon greater than 0 is given. By condition A, we can find epsilon naught, we can find n naught rather, n naught, such that this infinite sum, f n naught plus 1 plus f n naught plus 2, let me write it with a k, and let me write an infinite sum, f n naught plus k in absolute value. If you add it up all the way from k equals 1 to infinity, so this is again just the tail starting at n naught, that is going to be small. And how small do I want it? It turns out I want it to be less than epsilon divided by 2. So there's going to be another source of this error is going to appear twice. Okay, this actually doesn't make sense as a thing because this is a function and this is a number. What does it mean for a function to be less than a number? I actually want the integrals to be less than this. And that is really condition A is saying the sum of the integrals is small. The sum of the integrals is summable, so the tail gets arbitrarily close to 0. Make sure that the tail is less than epsilon over 2. Okay, so by condition A, I say of the definition of tilde equal. Okay, and now once we have this, again, we're going to use this actual idea over here. So I'm going to give this thing a name. So let Gn be defined by what? Gn, it starts out looking like f, so you do ordinary fn's up until n naught, and then you add on absolute values. And you add on, how many do? You do n of them. Okay, so it's the ordinary, the first looks a lot like f, but then we start adding on absolute values at the end. And the point is that Gn is going to definitely be bigger than f because we switched some of these things to absolute values, but it won't be too much bigger because of this control, right? Gn will be a little bit bigger than f, but not too much bigger, and that's what we want. Okay. Okay. So notice the Gn's are monotone increasing. They are monotone increasing. So this is where we're going to lock into the things we've done before. The sum of the f's could go up and down and up and down, and that's like we can't control that. But the Gn's, because of the way we define them with absolute values, are really going up, and that means we can apply the previous theorem. One other thing we need for the previous theorem, we need the limit of the Gn's to be positive. So notice also, the Gn is greater than 0, and by that I mean for all x. Gn of x is greater than 0 for all x, because basically Gn of x is greater than f1 plus dot 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 plus fn of x. Okay, let me write it without. All right, let's put the x's in. So fn, let's do fn naught, and then let's do fn naught plus 1 plus dot 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 plus fn naught plus n of x. So Gn is the same thing with the absolute values, so it's greater than what it would be if you got rid of the absolute values. And so now I take the limit of both sides, the limit as n goes to infinity. Okay, let's write it out as a step. Therefore, the limit as n goes to infinity of the Gn of x is greater than or equal to the limit as n goes to infinity of f1 of x plus dot 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 plus fn naught plus n of x. And this thing is getting really, really close to f of x. And f of x we said is greater than 0. That was given in the problem. Oh, I want the limit of this thing is greater than 0. So the Gn's, they're increasing and increasing, increasing. They end up at something that's bigger than f. And so because f is bigger than 0, the GNs end up being bigger than 0 too. Okay, this is actually not true for all x. This is only true for the x's where the sum is defined. For all x where the sum of the absolute value of fn of x is less than infinity, this is the condition B thing, right? This is the nice set from condition B. And that is where this thing equals that. Okay, so it's greater than 0 for all the x's that count. Okay. Fantastic. Okay, so the GNs are increasing. The limit of the GNs is greater than 0. And now we are in business. So now we apply the corollary we did. So by corollary 2.2.7, we have that the integral, the limit of the integrals is also greater than 0. The integral of Gn is greater than or equal to 0. So the GNs, we converted them to modified increasing, so their limit is greater than 0. And when their limit is greater than 0, we're going to show that this means the integral of the GNs is almost the same as the integral of f. And so we're going to get, except for that little epsilon over 2 we did at the beginning, we're going to get that the integral of f is greater than 0 as well. Okay, so there's a long sequence of inequalities in the book now. Now consider this following long sequence of inequalities. And it starts with 0 is less than the limit as n goes to infinity of the integral of Gn. Okay, and once again, I'm forgetting. Yeah, okay, yeah, there we go. And that thing is itself a sum. So this is the integral of f1 plus the integral of f2 plus dot 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 plus up to n naught. And then after n naught, it is a sum that switches to absolute values. So we do the absolute value of the integral of fk. Okay, and this thing, Gn is a finite sum of step functions, so the integral of Gn is the integral of the finite sum. So for finite sums, it's okay to flip things around. Okay, so 0 is less than that, is less than this. And this thing is a sum that is increasing in n. It's only getting bigger and bigger. The more you make n, because the things you're integrating are positive, it's just getting bigger and bigger. So I could just say it's less than the infinite sum. So I could say less than or equal to the integral of f1 plus the integral of f2 plus the integral of fn naught. And then I could say I have this infinite sum from k equals n naught plus 1 to infinity of the integral of the absolute value of fk. This was the thing that was less than epsilon over 2. We chose n naught to make sure that this whole thing was less than epsilon over 2. So already what this says is that the sum of the first n naught, it could be negative. It could be negative epsilon over 2, but it can't be really negative, right? And so we're pretty close. Like, as long as you believe me that this first little bit is close to f, we're quite close to proving the theorem. But we're going to fix it up. We're going to add on the infinitely many right now, and you're going to see that's going to introduce a second copy and upgrade that epsilon over 2 to an epsilon. Yeah, we're going to do that. It's going to be a big chain of inequalities. We're going to keep going. So you could stop here and sort of get most of what you want, but we're going to keep going and get everything we want. Questions or comments? So, yeah.
The index in the second last line, should it be at the top n naught plus n?
Yes, very good. So, okay, let's see. Yeah, okay, I think, you know what? I think the way I want to write it is like this. I want to do n naught plus k, and then I want this one to start at 1. But yeah, you're right. Something is wrong. I think I prefer to start at 1 so that when I do the limit, I'm going to later on do like an n naught goes to infinity type of situation, so it's a little bit easier to do it this way. But yeah, thank you for pointing that out. Very good. N naught plus k. Okay, great correction. Anyone else? Okay, let's add it on. So now what I'm going to do is, look, this thing is almost f, but I'm missing fn naught plus 1, fn naught plus 2, and so on. Let's add those on. And the problem is you can't just like straight add them on because they might be negative, right? And I'm doing a less than or equal to inequality chain. I can only make things bigger. So if I was just to add on the integral of fn naught plus 1, fn naught plus 2 to make f by continuing this infinite sequence, I would be cheating. So what I got to do is I'm going to add on something that for sure is non-negative. So it's going to be less than or equal to, and we're going to have the same thing again, f1 plus f2 plus dot 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 plus fn naught. And I would love to add on fn naught plus 1, fn naught plus 2, but those might not be positive. But you know what for sure is positive is this thing. I'm going to add on the integral of fn naught fn naught plus k. So right now I'm lying, right? I said it's less than this, but if this is negative, that's bad. No, not allowed. But if I add on the absolute value, now for sure it is positive. So you see I'm doing the integral of fn naught plus its absolute value. If it's a negative number, I'm adding on 0. If it's a positive number, then I'm adding on a positive number, right? A number plus its absolute value is something nice. X plus the absolute value of x equals 2x if x is bigger than 0, and 0 if x is less than 0, and this is greater than or equal to 0, right? X plus its absolute value is always bigger than 0, and so now I found a sneaky way to add on the integral of fn naught plus k. Even if it's negative, it's all good. And I'm going to do this. I'm going to do the infinite sum of these. K equals 1 to infinity. All right, so I've added that on. This is the integral of two things. I might as well do the integral of the two things separately. Okay? And now, if I add this tail, so I have the first n naught over here, and then I have the last infinity of them over here, that's the sum of the first infinity fn's. So this is the integral, let's call it j, so we see the difference. It really is the integral of the fj's, right? The first n naught are written out, and then the last infinity are written here. That's the integral of the fj's. And then what do I have left over? I got twice everything starting at n naught plus k, plus twice the sum from k equals 1 to infinity of the integral of the absolute value of fn naught plus k. Okay, very nice. Everyone with me? Good? Okay, last but not least, this thing is less than epsilon 2, and then this thing we chose to be less than epsilon over 2 by choice of n naught. Right? So what does our sequence of inequalities says? It says that 0 is less than the sum, the infinite sum of the integrals plus epsilon. And so therefore, minus epsilon is less than or equal to this infinite sum of j from 1 to infinity. So this could be negative. How negative could it be? It could be up to minus epsilon. But epsilon is arbitrary. Since epsilon arbitrary, therefore, 0 is less than this infinite sum. So a number that is greater than minus epsilon for every epsilon must also be greater than or equal to 0. And this is what we wanted to show. This is what is called the integral of f. Okay, that's the end of the proof. So you can see how the main idea in this proof was we're replacing the monotoneness, the weakly decreasing or increasing, we're replacing it with the absolute value by doing tricky tricks with absolute value and using the fact that the absolute values don't get too crazy. Because the absolute values were bounded by this epsilon over 2, this made the whole trick work. We replaced the function with its absolute value, and we didn't lose too much because the whole thing was added up to less than epsilon. Okay, questions or comments about this proof? This proof essentially is going to give us that the integral makes sense. So this is the corollary. This corollary I referenced a while ago, 2.3.3, and this says, our definition of the Lebesgue integral makes sense. It is well defined. Our definition of the Lebesgue integral is well defined. Okay, and mathematically, what does this mean? Well defined is this idea is if you do something one way and then you do it a different way, you should get the same final answer. So if you calculate the integral of some function f using your favorite sequence of step functions fn, and somebody else calculates the integral of f using their favorite sequence of step functions gn, even if you use different functions, if fn are different than gn, you should get the same final answer. So if f is equal to the infinite sum of the fn's, and f is also equal to the infinite sum of the gn's, so we have fn's in one corner, we have gn's in the other corner, and f is equal to both of them, then you get the same answer. Then the sum of the integrals of the fn's equals the sum of the integrals of the gn's. And this is great because this sum is what we're calling the integral of f, right? So the integral of f, it's not that it has two different numbers. There's only one possible number you could get. You could get to that number using two different sequences, but you're going to get the same final answer. Okay, and the proof is basically what we just did. The proof says, if these things are both equal to f, then their difference is greater than 0. And so this one will be greater than that one. And then well, it's going to be the reverse as well. It's going to be greater than or equal to 1. It's going to be less than or equal to the other. Let's see that. So the proof goes like this. So f is equal to f1 plus f2 plus dot dot dot. And f is also equal to g1 plus g2 plus dot dot dot. And now we alternate them. So we're going to subtract. We're going to do a big subtraction. Subtract to get. And we're going to get 0, which is f minus f. And we're going to alternate f1 minus g1, f2 minus g2. f1 minus g1 plus f2 minus g2 plus f3 minus g3 plus dot dot dot. Okay. Very technically, you would have to check, is it okay to subtract these things? I think we had an exercise that was about doing this. You technically have to check that the conditions A and B are satisfied. So condition A says, okay, we know the sum of the f's, the integral of the f's is fine. We know the sum of the integral of the g's is fine. Is the sum of f minus g, is that fine? Well, yeah, it's going to be bounded by what it was for the f plus the g. So technically, check. Good exercise. Check conditions A and B. But you'll see that in conditions A and B, this is all legit and all very, very easy. Okay, so 0 is this sum. And therefore, by the thing we just proved, by lemma 2.3.2 that we just proved, 2.3.2, what does this mean? If 0 equals that thing, well, then the integral of all this stuff has to be greater than 0. Therefore, the integral, and I'll write it like this, the sum from k equals 1 to infinity, and I'll do fk minus gk, that integral is greater than or equal to 0, right? So the infinite sum of this minus that is greater than 0. And if the infinite sum of this minus that is greater than 0, that means the infinite sum of fk minus the infinite sum of gk is greater than 0. Oh, okay. Again, this is another technical place. It's important both sums are finite. And again, this is by A and B. So like it could be, in general, it could be that this thing is true, but then when you split it up like this, you get infinity minus infinity, and then you can't do infinity minus infinity is greater than 0. But in this case, we know these infinite sums are finite by the conditions A and B. They once again imply that these things can't be infinite. These are finite numbers, so everything is legit. And therefore, the integral of the f's is bigger than the integral of the g's. Okay, great, we did it. So we wanted to prove, what did we want to prove? That the integral of, we wanted to prove the integral of the f's equals the integral of the g's. And I got to the integral of the f's is greater than the integral of the g's. So now we need another step. Can anyone think of what we should do now? I proved that the f's are bigger than the g's, but I want them to be equal. Yeah.
Flip it.
Yeah, just flip it. So you could say, oh, the f, which one was f and which one was g is arbitrary, or you could go back to this step, and I said 0 is f1 minus g1. I could have done 0 as g1 minus f1, and done it that way. So let's do it. Let's write that out. So now flip it. Now flip the argument to see 0 is equal to g1 minus f1 plus g2 minus f2 plus dot dot dot. And then I'll say, and the same argument gives the other inequality. The sum of the integrals of the gk are greater than or equal to the sum of the integrals of the fk, right? And again, 0 is both greater than 0 and less than or equal to 0, so that's why the things work out. So now we have inequalities both ways, and therefore the integrals are the same. Therefore, okay, and then we're done. Okay, so this finally proves that our definition of the Lebesgue integral, which says approximate it by step functions, but in this weird way, it actually makes sense. You get a final answer that does not depend on the particular choice you found. Any sequence of step functions that is converging to some function f will have the same integral, And so it's a legit thing to do. And so the textbook says, they call this space L1, like we kind of have been. So the definition, L1 of R is the set of functions f where the integral of f is less than infinity, right? Where the integral of f means this, you mean can find step functions f1, f2, dot, 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 such that f is like this, right? So anytime you have a function that can be written as a sum of step functions in the way we said, then you can find its integral. Its integral is the limit, it's the sum of the integrals of the step functions, that infinite sum. And that is a space called L1 of R. And that space is a vector space. So this is theorem 2.3.4. L1 of R is a vector space. Is a vector space. And a vector space, remember, means it's okay to add things, it's okay to scalar multiply things, and the integral will respect that. So they write this as, they say the integral is a linear functional. And linear functional means it respects sums and scalar multiples. So the integral of f plus g. So first of all, if f is in L1, f in L1 of R, g is in L1 of R, that implies f plus g is in L1. And not only that, if you do the integral of f plus g, you get the integral of f plus the integral of g. And it's the same thing for scalar multiplication. If f is in L1 of R and lambda is some number, then lambda times f is also in L1. So then lambda times f is in L1. And the integral of lambda times f is lambda times the integral of f. So integrals do what you would think. They behave linearly. If you add up two things that are integrable, it's still integrable. You can do addition and scalar multiplication. And the proof is the following. Okay. So the first bit is that the integral is well defined. We did that. And then the second bit is to do addition. So if you have, let's say addition. Let's do this. So you have f is in L1 and g is in L1. And we would like to conclude that f plus g is in L1. Okay. If f is in L1 and g is in L1, what do we know about f and g? Well, what can we do? This is again, we have to unpack what we know about f and g and use that to get to what we want. Yeah?
You can integrate both of them?
You can integrate them, yeah. How do you integrate them? What does it mean to do the integral? Yeah, this is the tricky thing, right? In the Riemann integral, it's like you take some slices of the thing, but for our integral, what does it mean that we can integrate? Yeah.
So the conditions A and B from earlier are satisfied.
Yeah, so you can find step functions, can find f1, f2, dot, dot, dot. So there must be some approximation of the f's by step functions. And f is f1 plus dot, dot, dot. And all the conditions A and B are baked into this notation. This sim equals means we find the step functions. They are step functions. And they satisfy the properties A and B are baked into this. F is that thing. Same for G. We can also find GNs, G1 plus G2 plus dot, dot, dot. So we can find F1, F2, and G1, G2, and so on. F is made of step functions, G is made of step functions, and everything works. Okay, we'd like to conclude that F plus G is in L1. How are we going to prove that F plus G is in L1? Well, if you know something is in L1, then you get a sequence of step functions. If you want to prove something is in L1, how would you do it? Yeah?
Find that sequence of step functions.
You have to find a sequence of step functions. Okay, we have some ingredients over here. Do you think you could come up with what are the step functions that together would make F plus G? Yeah.
We just add F1 and G1, F2 and G2, etc.
So notice F plus G, it's going to be the sequence F1 plus G1 plus F2 plus G2 plus F3 plus G3 and so on. Okay. Now, once again, this symbol is not equals, right? This symbol is the crazy equals that means you have conditions A and B. So this is a really good exercise. Please check. Must verify A and B. This is the kind of very Very good exercise. A, B, right? We know A and B hold for the F's, right? We're sort of given that A and B hold over here. We're given conditions A and B, and we got to check conditions A and B for this sum, right? And it will work. It's some very simple thing. They're like, oh, this sum is finite, that sum is finite. Why is the sum of the sum is finite? That kind of stuff. But very good exercise to try to check. So good practice. I will leave it as an exercise. Good exercise. Okay. It's not too hard, and it's one of those things that works out the way. There's only one way it could work out, and it works out that way. So it's not, kind of worth doing. It's good for you to try to see like, oh yeah, it works. But if I just show you, you'll be like, oh yeah, of course it worked. Okay. F plus G is this thing, and therefore F plus G is in L1. Okay, and not only that, the integral of F plus G will be equal to this infinite sum, n equals 1 to infinity, the integral of these things, Fn plus Gn. And when you only have two of them, you can split it up as the integral of Fn plus the integral of Gn, because you just have finitely many pieces. And then you have the infinite sum of two things. Both things sum up to finite numbers. So since both are finite, then you get this infinite sum of the Fn plus the infinite sum of the Gn, which is also known as the integral of F plus the integral of G. Okay, so it all does what you think. If you can approximate F and G individually by step functions, you can approximate F plus G by adding up the step functions from F with the step functions from G, and then everything will work out. Okay, let me leave the other one. The other one is a good exercise as well. Let me leave that as well. So part two is given F is in L1 and lambda in R, prove that lambda times F is in L1 and that the integral of lambda times F equals lambda times the integral of F. Okay, why is this true? Good exercise. Please try it. Okay, and this is a really good practice with, in this course, what does it mean to be in L1? Right, you have to use the definition as part of what you're given, and as part of what you're checking, you need to know both sides. Okay. Now we have the Lebesgue integral. So we finished section 2.3, and we're gonna move on to more and more powerful things. Like, what is the whole point of the Lebesgue integral was that it was better than the Riemann integral. Now we have it. We're gonna start proving properties of it that are better and better. This is a great place to stop for questions or comments or anything else. Yeah.
Are we heading into the next chapter of the text?
Yeah, we're going into the next section. So we just finished 2.3, now we're going to do 2.4. Chapter 2 has a lot of sections we will not do. So we're actually more than halfway done chapter 2. And then in chapter 3, we're going to go back to the thing we did on the very first day of looking at the space L2. So we're doing L1 right now. When we do L2, it turns out L2 will use the same integral. Everything will be fine for integrals, but L2 has this extra inner product structure. So that's a big picture of what we're doing. We're going to build up some more theorems. Basically, we want theorems that say, this is the next up. So we're going to have Fn going to F when does, and in what sense, imply the integral of the Fn converges to the integral of F. Okay? This is the main kind of thing we want to answer. We want to know, if I look at a sequence of functions and they're converging to something, do their integrals converge? And we have a couple of these already, right? Like when the Fn's were step functions, and when we had like monotoneness or like some kind of nice sum, then we would have this kind of conclusion. But we want to make it a little bit more general, and we want to upgrade to the Fn's not just being step functions, but any function. And then we'll when we prove these, then we'll be ready to do L2 and all the proofs there. Yeah.
I probably just forgot that we did it, but in like the above proof for the addition,
Yeah.
we're like assuming that it's like linear on step functions, right?
That's right. Yes, that's right. So for example, in this step, we were using the linearity on step functions, and that is a lemma in the book. Linearity on step functions, and that was in I think section 2.2. 2.2, yeah. So if you go into section 2.2, it's all about step functions, and with some lemma, we were like, oh, it works. The reason it works, again, is because everything is finitely many pieces, right? Every step function is a finite sum of rectangles, And you have a finite sum of rectangles, you can reorganize the sum in all sorts of ways. So do you want to add up the whole rectangle or the bottom half and then the top half? We're going to get the same answer, right? So for finite sums, it's sort of like obvious, quote, and then for infinite sums, that's where all the proofs had to happen. Yeah, great question about where we did that. Yeah, okay. And yeah, you're also going to need that for this exercise. You're going to need an analogous property for step functions. Okay. Other questions or comments? Okay, so the first thing we're going to do, I think the first proof in 2.4 in the last little bit here. So section 2.4 is called the absolute value of the integral. And the first thing you might notice is I called this space L1, and I said that it is a vector space, right? L1 is a vector space. Vector space means you can add things together, you can scalar multiply, but not only is L1 a vector space, it is a normed vector space. So this is the goal. The goal, we're going to make a norm on L1 of R. And the norm is going to be what we kind of hinted at earlier in the course. It's going to be the absolute value of f, and then you integrate that. And when you integrate the absolute value, that means that all the negative parts become positive. And so like if f is positive then negative, then positive then negative, then it definitely can't be 0. So we integrate up the absolute value. So this is going to be a norm on L1 of R, and we have to do it. The issue is, right now, the way we have defined it, f being integral says something about the integral of f. What about the integral of the absolute value of f? What if the integral of the absolute value of f doesn't even exist at all? So problem. F in L1 of R means the integral of f exists, right? And it's that infinite sum of step functions. What if the integral of absolute value of f does not exist? Does not exist. And you might think, oh, this is kind of like a silly thing to worry about. But for example, in the Riemann integral, if you do this integral, this is the example from the textbook. If you do the integral of sine of x over x dx, this is some number in the Riemann land. So this is Riemann integrable. Riemann integrable. Sine of x over x is Riemann integrable from minus infinity to infinity. Once again, the definition for Riemann integrable is when you do minus infinity to infinity, what you're actually doing is you are actually doing some finite integral and then taking the limit. So you go from minus L to L, and then you do the limit as L goes to infinity, right? So the Riemann integral does integrals by splitting them up into some finite piece, chopping up the pieces really fine, and then taking the limit. And this one is integrable, but if you do the absolute values, it's not integrable. But, and once again, let me write it as a big limit to make it clear what's going on. So for Riemann, from minus L to L, if you take the absolute value, let's make the absolute value purple, sure, sine of x over x dx, that is actually infinity. So in the Riemann land, the thing we're about to do doesn't work. This is already one nice upgrade of the Riemann integral, and it will work for Lebesgue. So for Lebesgue, we will see that this never happens. For Lebesgue, this is okay. And so the actual theorem we're going to do, theorem 2.4.1, it says if f is in L1 of R and f is given by some sequence of step functions, then the absolute value of f is also in L1. So good news, the thing we just said doesn't work in Riemann. It's always good in Lebesgue. If f is in L1, then the absolute value of f is also in L1. And not only that, we have a nice inequality. And the inequality says the absolute value of f sandwiches like this. So if you add up all the individual pieces, you add up the absolute values of all the individual pieces, that will be no more than the integral of the absolute value of f. And this thing is the thing that was finite by condition A, right? So remark, this is less than infinity by condition A. So this is a little remark. So there we go. Good news. Everything works very nicely for absolute values. Okay. What do I want to say about this proof? Okay, here's what we're going to do. We have 10 minutes left. This proof is, there's one idea that is like nice, and then the rest of it is like not very interesting. So I'll tell you the nice idea in the last 10 minutes, and then we'll say that's good enough. And then we will, if you want to read it, you can read it. Otherwise, we're going to use it. Okay, so the proof. Okay, so what do we have? What do we have? We know f is in L1, and we have this sequence. F is like f1 plus f2 plus f3 plus dot, dot, dot. And like, for example, f is the limit of all these f's, except for on this bad set, right? So the limit as n goes to infinity of the sum from k equals 1 to n of fk of x equals f of x for x not in the bad set. So this stupid bad set is quite annoying in this proof. You have to write down the bad set, and then everything you say, you're like, oh, it only works not on the bad set, and so on. But it's kind of a technicality and not super exciting. What would be the absolute value of f? Well, I'll tell you what would be the absolute value of f. If we do the absolute value of f of x over here, then what you should do is the limit as n goes to infinity of the absolute value of this thing, right? This is just like continuity of the absolute value function. So notice this. Now, when you write a function f, it's not enough to have a sequence that's converging to it. You've got to write this thing as a sum. So we have to write this as a sum. Write this as an infinite sum. Okay? And the way you write something, if you have a sequence of things and you want to write it as a sum, you just subtract them from each other, and that will make the sum. I think we did this trick at one point in the course. So let's call this thing Sn. So let's call this thing Sn of x. This little colon equals means whatever is over here. That's the definition of Sn. So Sn of x equals this absolute value. So we know the limit as n goes to infinity of Sn of x equals the absolute value of f of x. And I'm going to write the Sn's now as a big infinite sum. It's a very silly little sum. Okay, everything I said is fine, except for the way I defined Sn was different than the textbook. So let me fix it. The stuff inside the absolute value of is the Sn. So this whole thing is Sn, and the limit of the absolute values of the Sn's are f. And so what I'm going to write the absolute value of f of x. I'm going to write it like this. It's S1 in absolute value plus, and then you do S2 of x minus S1 of x. And then you do plus S3 of x in absolute value minus S4 of x. Okay? And plus dot, dot, dot. So f is the infinite sum of the absolute value of the Sn's. And so I'm going to write it as the first bit plus the difference of the second bit minus the first bit, plus the third bit minus the second bit, and so on. Did this 2 maybe came out a little funny. So this is this telescoping sum idea that I think we've had earlier in the course. Telescoping sum idea, right? You can write something as a telescoping sum, and they call these things G. So they say this thing, we're going to call this thing, we're going to call whatever absolute value of this thing is, we're going to call that G1 of x. The difference of the absolute values, S2 minus S1, we're going to call that G2 of x. This one will be G3 of x. In general, Gn of x equals the absolute value of Sn of x minus the absolute value of Sn minus 1 of x, right? So by doing the difference of the absolute values, Sn is some crazy weirdo sum of step functions, but it's still a step function. And so the absolute value is a step function, and the difference of step functions is still a step function. So Gn is some like horrible tortured mixture of step functions, but it's still a step function. And notice that the limit as n goes to infinity of Gn of x as a sum, okay, I want the sum of the first n, k equals 1 to n, that equals the limit as n goes to infinity of the absolute value of Sn of x, and that equals the absolute value of f. Okay, and again, except for x on the bad set. So there's all these little technicalities you got to do, but this is the idea. You create the sequence of step functions for absolute value of f by taking these absolute values and doing the telescoping trick, and everything will work out. So there is, and it's work. It really is some inequality stuff. It's not as simple as the exercises I will do, but they do it in the textbook. So this is work done in textbook, and it all works out. So it all works out. And you prove that the absolute value of f is really equal to this sequence of g's. g1 plus g2 plus dot dot dot. And it's all good. And so the integral of f equals the infinite sum of the integrals of g, integral of gn. And this thing, it turns out, the integral of the gn's is going to be less than the integral of the absolute value of the fn's, again, by some work. Okay, so some inequality work. Okay, and I think it's not super instructive here, so I think if you want to see the proof, you can read it. Otherwise, we'll leave it like that, and we're going to move on to section 2.5, which is more exciting on Thursday's class. Okay, this is a great place to stop for now. We have 5 minutes for questions or comments if anyone has one. Otherwise, please feel free to come up if you also want to ask me. And we'll see you on Thursday for another lecture.